Hi. This video serves as an introduction to the concept of the antiderivative, which is also known as an improper integral. Alright, so if the d dx of capital F of x is equal to little f of x, then we would say the derivative of capital F is little f. We've already talked about that a lot this quarter, right? Well, now we're going to flip it around. That's why instead of taking the derivative, we're going to go backwards and undo the derivative. That's what we call the antiderivative. So if the derivative of capital F is little f, then that means that the integral of little f of x is capital F plus some constant. We'll talk about this constant in a second, but first I want to get you used to the terminology. Okay, so if the derivative of capital F of x is little f of x, that's the same thing as saying the antiderivative, which is the opposite of the derivative. The antiderivative of little f of x is capital F of x. Okay? So the antiderivative is just the derivative backwards, and it's expressed using this elongated s notation. This long-looking s right here is called an integral. And the antiderivative is synonymous with what we call the improper integral. Right now, for short, I'll often call this the integral, and later you'll learn the difference between proper versus improper integrals. So this is read as the integral of little f of x dx is equal to capital F of x plus c. Please note that whenever you're writing an integral, you start writing an integral with the long integral sign, and you finish with writing the dx. This little dx right here is the differential, which is the same differential that you see on the derivative in the d dx notation. Think about writing an integral kind of like how you would write something with a set of parentheses. Now you would never write an open parentheses without finishing it off with a closed parentheses, right? That's the same thing that we have with an integral right here. Please note, when you start an integral, you open the parentheses with the integral sign, and then you close it off by writing the dx right here. So make sure that every time you write an open integral, you close it off by writing a dx at the end. Those two go hand in hand. Alright, now let me explain the plus c. Why is the antiderivative of little f of x equal to capital F of x plus any constant? Well, that's because the derivative of any constant number is 0. Right? So when I say the derivative of f of x of capital F is little f of x, that's actually also true. This would be a true statement if I added any constant value to that capital F of x. You see, by the addition rule of derivatives, the derivative of capital F would be little f, and the derivative of any constant number that I add, here the plus c stands for any number, 1, 2, minus 7, 84, any number you can think of. The derivative of all numbers is 0, right? So this is going to disappear when I take the derivative. Well, that means that when I take the antiderivative, it turns out that I could have had any plus c there. Actually, I wouldn't have known what, if any, constant multiple I had added here. Constant additive term. Because when I took the derivative, that plus c disappeared, right? So when we go backwards and we take the antiderivative, we have to account for that fact so that all antiderivatives include a plus c term. Alright, now let's think about this visually. Okay, as we talked about it before, the derivative represents the slope of the tangent line or the instantaneous rate of change of a function at all points. So let's say that we have this blue curve, x squared, and then the derivative of x squared, as we know, is 2x. That's the same thing as saying that if I consider any point on this curve right here, and I draw a tangent line, like, look, there's a horizontal tangent right there. The slope of this horizontal tangent at x equals 0 is 0. It's totally horizontal. So that means that the derivative goes through the point 0, 0 right there. Now if I consider the tangent line over here for some positive value of x right here, you can see that the slope is positive. And that corresponds to having a positive value of the derivative right there. Likewise over here, if I draw a tangent line, you can see that that slope is negative, and sure enough, the derivative is negatively valued over there. Okay, so we recall that the derivative function represents a plot of the slope of the tangent line at all the points that we considered for x up here. Okay, the derivative of x squared is 2x. That's the same thing as saying the antiderivative or integral of 2x is x squared plus c though. Because if I tell you that I have a function whose derivative is 2x, what's the function? You'll say, oh, well the function is x squared because the derivative of x squared is 2x. But that's not the only function whose derivative is x squared. Actually, you see all these functions, all these smiley faces right here? These all have the same exact derivative. Each one of these things has the derivative x squared. If I take the derivative of x squared, the derivative is 2x, right? If I take the derivative of x squared plus 1, the derivative is still 2x. If I take the derivative of x squared minus 2, the derivative is 2x. That's where the plus c comes from, because no matter which vertical translation of that parabola I choose, the slope of the tangent line will always be the same. Like for instance, at the point x equals 0, horizontal slope, horizontal slope. Look at the tangent lines on each of the functions in this whole family of functions, which are all vertical translations of each other. They all share the same slope on their tangent line at a given value of x. That's why they all share the same derivative, and that's why the antiderivative must include the plus c term. In this series of videos, we're going to learn a lot about how to find antiderivatives, and when we're taking the antiderivative or improper integral, please do not forget the plus c term.